In this particular problem, we are once again going to use static equilibrium principles, but here there are two unknown forces. Previously, we did not know a single force and we did not know its angle. In this particular case, we do not know either force, but we do know the angles. The find statement here only requires, however, that you find one of those forces, F4 required for static equilibrium. As before, you will need a sign convention and you will need to label all of your variables. A couple of things to point out here. First of all, you may not be familiar with the KIP unit. KIP stands for kilopounds. That is a US customary unit, pounds, with a metric prefix, kilo. At this point in time, you'll see I already wrote applying static equilibrium to the x direction, but what I would encourage you to do is first look at the problem and look in the x direction. How many unknowns are in the x direction? In this case, F1 has an x component that is unknown, and F4 has an x component that's also unknown. That's two unknowns. In the y direction, then, if we analyze the y direction, we know F3y, we know F2y, we don't know F1y, we don't know F4y. So once again, two unknowns in the y direction. It behooves you to determine if there are any directions in which there are fewer unknowns. So for example, if there was only one unknown in the x direction, I would want to start with that. In this case, since there are two unknowns in the x and two unknowns in the y, it doesn't really matter where I start. So I will start with the x direction because that's just my habit. You must start by first stating your assumption. In this case, we are assuming that the sum of the forces in the x direction equals 0. Now we have our 0 statement. Now we need our where statement. F1x is going in the negative direction, and it is a negative cosine alpha times F1. F2x is going in the positive direction, and its value is a positive cosine beta times F2. F3x is also going in the positive direction. It is a positive sine gamma times F3. You'll notice that the angle for F3 is actually marked off the y-axis. There's nothing wrong with that, but keep in mind that cosine does not mean x. Cosine means adjacent side, so in this case the adjacent side of that 20-degree angle would be the y. The opposite side would be our x side, which in this case is sine. And F4x is going to be a negative cosine delta times F4. For F1 and F4, you might ask, which one of those do we want to use? There is one unknown on the right side. There is also one unknown on the left side. In this case, we're going to have two unknowns in this equation regardless of what we do. Either we're going to have F1x and F4x, or we're going to have F1 and F4. Because we do know alpha and we do know delta, so that's not an unknown. You need to use the right side of this equation. And the reason for that is because when I develop my y equations, I will have some function times F1 for the y component. I want F1 and F4 to be common between both equations, so I'm going to end up with two equations and two unknowns. If I use F1x and F4x here in this equation, and then use F1y and F4y in my y equation, I would end up with two equations and four unknowns, and I would not be able to solve that. The general rule of thumb is you need at least as many equations as you have unknowns. So if you have two unknowns, you're going to need at least two equations. If you have three unknowns, you will need at least three equations. Plugging all of this stuff into this equation, and we have the equation fully developed there. Now, at this point in time, you'll notice we don't know F1 and we don't know F4. We have two unknowns. It is recommended that you don't do anything to that equation. I'm going to write a letter A next to it. I'm going to label it as equation A. And the next line I'm going to write is equation A has two unknowns. Once again, those unknowns are F1 and F4. And then I'm actually going to stop. Now that I've finished the x direction, I'm going to do the same thing with the y direction. I'm going to make my assumption of static equilibrium and provide a 0 statement. In my where statement, I will say what each of these components are. F1y is going in the positive y direction, and its value is sine alpha times F1. F2y is going in the negative direction, and its value is sine beta times F2. F3y is going in the positive y direction, and its value is cosine gamma times f3. And f4y is going in the negative y direction, and its value is negative sine delta times f4. Once again, I'm going to want to use the right side of all of these terms so that I have f1 and f4 common between my x equation and my y equation. Since I have two unknowns, f1 and f4, I label this equation. I'm going to call it equation B. And once again, I'm not going to do anything else to that equation. I'm just going to leave it in that format, and you'll see why shortly. At this point in time, I can actually go ahead and solve for f4. What I'm first going to do is write both of the equations down that I already found. Now, this is not the only method you can use to solve these problems. It is only one method. You're not required to use this method, but this is what I'm going to show you. I'm going to solve for f4 directly here. You could, of course, solve this first equation for f1 and then plug that into f1 in the second equation. But in my experience, that tends to lead to algebraic errors. It's quite a bit of algebra. So what I'd rather do is cancel out f1 entirely. You see, I have a negative f1 in the first equation and a positive f1 in the second equation. I want to get this coefficient the same for both of them, so when I add the top equation to the bottom equation, those two numbers cancel out. In this case, I've got a sine alpha in the bottom and a cosine alpha in the top. And the easiest way to do this is probably to multiply this top equation by tangent of alpha. Tangent is sine divided by cosine. So if we multiply cosine by sine divided by cosine, the cosines cancel out and we're just left with sine on the top. The only tricky thing that you need to remember about this is you have to multiply each term in this top equation by tangent alpha. This first term just becomes sine alpha times f1. The second term becomes tangent alpha times cosine beta times f2. The third term becomes tangent alpha times sine gamma times f3. The fourth term becomes tangent alpha times cosine delta times f4. Now at this point in time, I've got a positive sine alpha times f1 up here and a negative sine alpha times f1 down there. So if I take these two and if I add them, here's what I get. And I like to group my like terms together, so I would typically write that equation this way. After I'm done with that, I need to solve this equation for f4. So I would add this whole term to both sides, and then to get f4 by itself, I divide both sides by this trig stuff over here. And now we can plug our numbers in, and f4 is going to equal a positive 2.49846 kip. Once again, since we've used static equilibrium here, that positive sign doesn't mean positive direction. That positive sign means we assumed correctly. It is actually going down into the third quadrant at delta equals 40 degrees. Now a couple of notes. In this example, I only solve for f4. To find f1 would be pretty simple. You just take f4 then and plug it back into one of your equations, either equation A or B, and you'd be able to find the other variable. Also, you may wonder, well, what happens if we get a negative sign? Well, we're already constrained on our angle. But if we got our negative sign, that means we drew it in the wrong direction. So if we would have gotten a negative sign for f4, that would have meant that f4 is actually going this way at 40 degrees. However, that's not the case here. We get a positive sign. So here's our answer. And that is what you would do if you have two forces that you need to solve for static equilibrium and you don't know either of them.